Somewhere behind you, light years away, is a planet your people destroyed. Somewhere ahead, light years distant, is a world your descendants might colonize. You will see neither. You are born, live, and die aboard a generation ship, trapped in the narrow metal corridor between yesterday's failure and tomorrow's hope. If you love diving deep into the grand mysteries of space, make sure to hit that subscribe button. We explore the cosmos together every day. Now let's get started. With current technology like the Parker Solar Probe, humanity's fastest spacecraft, a trip to Proxima Centauri would take roughly 6,300 years, 6 millennia. 6,000 years ago, humans were just beginning to build the first cities. Writing hadn't been invented yet. The pyramids of Egypt were still 3,000 years in the future. Now imagine that entire span of time spent inside a single spacecraft. This is where the generation ship concept emerges. If we can't make the journey fast, then we make it long. We build massive habitats, kilometers into length, rotating to simulate gravity. We pack them with people, animals, plants, and all the technology needed to sustain a closed ecosystem for centuries. The original crew launches, they live their lives, have children and die. Those children grow up, have their own children and die. Generation after generation, the population lives entirely within the ship until, hundreds or thousands of years later, their distant descendants finally arrive at the target star. It sounds almost poetic, like an ark carrying humanity's future across the stars. But when you dig into the science, the poetry fades and the horror sets in. Let me take you through the reality. First, let's talk about the people. How many humans do you need to sustain a healthy population for centuries? Early estimates were optimistic. Some researchers suggested as few as 150 people could be enough, but those estimates didn't account for genetics. In 2021, a team led by astrophysicist Frédéric Marin at the University of Strasbourg published groundbreaking research using Monte Carlo simulations to model the genetic evolution of populations on generation ships. They included the entire human genome, 46 chromosomes, and simulated processes like meiosis, crossing over, and mutations caused by cosmic radiation. Their conclusion? To avoid catastrophic inbreeding and genetic drift, you need at least 10,000 people. 10,000, and if you want to be truly safe, if you want genetic diversity robust enough to handle the unpredictable stresses of space, you're looking at 40,000 people. 40,000 humans living, working, reproducing, and dying inside a single spacecraft for millennia. Now, think about what that means. You need to build a habitat large enough to house 40,000 people, not just cram them into bunk beds, but give them space to live, to farm, to manufacture goods, to move around. You need schools, hospitals, workshops, recreational areas. You need kilometers of corridors, life support infrastructure, power systems. The spacecraft becomes a city, and cities need resources, lots of them. This brings us to the second nightmare, life support. On Earth, our biosphere is an open system. Energy pours in from the sun. Plants absorb carbon dioxide, release oxygen and grow. Animals eat plants, breathe oxygen, and exhale carbon dioxide. When waste is produced, it decomposes, returning nutrients to the soil. It's a cycle refined over billions of years. A generation ship must replicate this cycle in a closed system. Every molecule of oxygen, every drop of water, every gram of food must be endlessly recycled. There is no resupply, no spare oxygen tanks arriving from Earth, no backup water reserves. If the system fails, people die. And here's the brutal truth. We don't know how to build a truly closed-loop life support system that works for centuries. The International Space Station has been testing regenerative life support for over 2 decades. Systems like the oxygen generation assembly split water into hydrogen and oxygen. The carbon dioxide removal assembly scrubs the air. Urine is recycled into drinking water. But even with constant monitoring from mission control on Earth, regular resupply missions delivering spare parts, and crews trained to repair and maintain every component. These systems require frequent interventions. The Life Support Rack, Europe's advanced closed-loop system launched in 2018, was designed to last 10 years. It failed after 6, filters clogged, pumps broke, sensors malfunctioned, and this was as on the ISS, where astronauts could call home for help, where replacement parts arrived every few months. On a generation ship, there is no home. There are no replacement parts. There is only what you brought with you, and once it's gone forever. And if you think you've heard terrifying stuff already, you need to check out my video called "What Actually Kills You on the Journey to Alpha Centauri?" Because we dive into the brutal physics of interstellar space, from radiation storms to micrometeorite impacts. And trust me, the universe is not kind to fragile human bodies hurtling through the void. The link is in the description and pinned on the comments. Now let's dig deeper into the life support crisis. Imagine you're an engineer aboard this generation ship, 300 years into the journey. Your great-great-great-great-great-grandparents designed the water recycling system. It's been running for centuries. Filters have been replaced, pumps have been repaired, but now you're facing a problem no one anticipated. The membranes that separate contaminants from clean water are degrading in ways the original designers never predicted. Maybe it's because of the constant bombardment of cosmic radiation. Maybe it's because the synthetic materials are breaking down chemically over time. Whatever the reason, the filtration efficiency is dropping. 10%, 20%, 30%. You try to compensate by running the water through the system multiple times, but that uses more energy, which strains the power grid, and the power grid has its own problems. Energy is the lifeblood of a generation ship. Without power, the air recyclers stop, the lights go out, the temperature plummets, the food production systems collapse. So where does the power come from? Solar panels won't work once you're far from the sun. Beyond the orbit of Mars, sunlight becomes too weak to be practical. That leaves nuclear power. Fission reactors, most likely. The technology exists, but nuclear reactors require fuel, and fuel rods decay. They need to be replaced. On Earth, we manufacture new fuel rods in specialized facilities. On a generation ship, you'd need to bring all the fuel for the entire journey, or you'd need the industrial capacity to reprocess spent fuel into new fuel rods. And fuel reprocessing is chemically complex, requires high temperatures, and produces radioactive waste. Where do you store that waste for thousands of years? How do you keep it from leaking into the habitat? These are not hypothetical questions. These are engineering realities that have to be solved before the first bolt is welded, and then there's food. Agriculture in space is vastly different from agriculture on Earth. You can't just plant seeds in soil and wait for rain. You need artificial lighting, which consumes enormous amounts of energy. You need precise control of temperature and humidity. You need to manage pests and diseases without the ability to introduce new species or chemicals from outside. The closed ecosystem means every organism you bring with you, every bacterium, every fungus, every insect, becomes part of the system forever. If a blight wipes out your wheat crop, you can't order new seeds from Earth. If a parasite infects your chickens, you can't bring in veterinary medicine from the outside. You have to solve the problem with what you have, or you lose that food source permanently. NASA's research into bioregenerative life support systems shows that maintaining stable, productive ecosystems in confined spaces for even a few years is extraordinarily difficult. Now multiply that challenge by centuries. Let's talk about failure modes. In engineering, a failure mode is a way something can go wrong. Every component, every system has multiple failure modes. A pump can seize up, a valve can stick open, a sensor can give false readings, a computer can crash. On Earth, when something fails, you replace it or repair it. On a generation ship, you have limited spares. A study conducted by NASA Ames Research Center on ultra-reliable life support systems found that to achieve the reliability necessary for a decades-long Mars mission, you need to carry spare parts equal to roughly the mass of the original system. For a generation ship traveling for millennia, the mass of spares required becomes astronomical, and even with spares, you're gambling that future generations will have the knowledge and skill to make repairs. What happens if critical expertise is lost? What if the person who understands how to repair the reactor dies in an accident and their apprentice is still learning? What if a plague sweeps through the crew and key engineers are among the casualties? This brings us to one of the most underappreciated dangers of generation ships: knowledge decay. Human knowledge is not automatically passed down. It requires teaching, learning, documentation, practice. On Earth, we have universities, libraries, the internet, millions of people contributing to the preservation and expansion of knowledge. On a generation ship, you have a few thousand people, isolated from the rest of humanity, with no new inputs, no new discoveries arriving from the outside. Studies of isolated communities on Earth show that technological and intellectual regression is a real risk. If the crew becomes complacent, if education falters, if people lose interest in maintaining complex systems they don't fully understand, the ship's technological base can erode. Imagine trying to explain quantum mechanics or molecular biology to someone who's never seen Earth, who's never experienced anything beyond the metal corridors of the ship. Imagine trying to motivate them to study advanced mathematics when their world is so small, so unchanging, that curiosity itself begins to wither. And that's where the psychological nightmare begins. Let's talk about the mental health crisis that would inevitably unfold on a generation ship. We have decades of research on the psychological effects of isolation and confinement. NASA's Behavioral Health and Performance Research Program has studied astronauts on the International Space Station, on long-duration missions in space, and in ground-based analogues like the Mars 500 simulation. That was a study where 6 men were sealed in a mock spacecraft for 520 days to simulate a mission to Mars. 520 days, not 520 years, and even in that relatively short time, the crew experienced severe psychological stress. One crew member showed symptoms of depression in 93% of mission weeks. Conflicts with mission control were reported 5 times more often than conflicts among crew members. 2 crew members developed chronic sleep problems, leading to persistent fatigue and cognitive deficits. Another crew member became so socially withdrawn that he barely interacted with the rest of the team. And this was with only 6 people in a controlled environment, with the knowledge that the experiment would end, that they would walk out and return to normal life. Now imagine a population of thousands confined to a ship, knowing they will never leave, knowing their children will never leave, knowing their grandchildren will never leave, for generation after generation. The psychological toll would be catastrophic. Humans evolved on Earth. Our brains developed in environments with open skies, varied landscapes, changing weather, the rhythms of day and night tied to the sun. We're wired for novelty, for exploration, for social interactions with diverse groups of people. A generation ship is the opposite of all of that. It's a monotonous, unchanging environment. The same walls, the same faces, the same routines day after day, year after year, decade after decade. Research on sensory deprivation and social isolation shows that humans begin to experience cognitive decline, mood disorders, anxiety, and even hallucinations when deprived of environmental stimulation. Boredom, monotony, and lack of purpose are not trivial problems. They are existential threats to mental health. And then there's the social structure. How do you govern a population on a generation ship? Who makes the decisions? What happens if the crew disagrees about the mission? On Earth, If you don't like your government, you can move to another country. On a generation ship, there's nowhere to go. You're stuck with the social and political system you were born into. History shows us that confined populations under authoritarian control can experience severe human rights abuses. What's to stop a generation ship from devolving into a dictatorship? What's to stop factions from forming, conflicts from escalating into violence? There's no police force you can call, no external authority to intervene. The crew has to police itself, govern itself, and resolve its own conflicts. And if they can't, if society breaks down, the mission fails. Everyone dies. Let's consider reproduction. In a closed population, who gets to have children? If the population grows too fast, you run out of resources. If it grows too slowly, genetic diversity collapses and the population crashes. You need strict reproductive controls. That means some people will be told they cannot have children, or they can only have one child, or they must have children with specific partners to maintain genetic diversity. Think about the ethical nightmare of that. Think about the loss of personal freedom, the psychological impact of being told your reproductive choices are not your own. And what happens if people refuse? What if they have unauthorized children? Do you force abortions? Do you exile them? Where? There's nowhere to go. The ethical dimensions of generation ships spiral into territory that most scientists prefer not to discuss publicly, but we need to confront them head-on. Because when you strip away the romantic vision of humanity spreading among the stars, you're left with a fundamental moral question. Is it ethical to condemn thousands of people to live their entire lives in confinement for a mission they never chose? Think about it this way. The original crew, the pioneers who board the ship on Earth, they're volunteers. They know what they're signing up for. They've weighed the risks, they understand the sacrifice, and they've made a conscious choice to participate in something larger than themselves. But what about their children? What about the generations born 100 years into the journey, 200 years, 500 years? These people never agreed to anything. They were born into captivity. They have no choice but to live out their lives inside this vessel, performing roles assigned to them by the needs of the mission, following rules established by ancestors they never met, all in service of a destination they will never see. From a philosophical standpoint, this raises profound questions about consent, autonomy, and the rights of future generations. Some researchers have called this generational tyranny. You're imposing the desires and decisions of one generation onto all subsequent generations, with no mechanism for those future people to opt out or change course. What if, 300 years into the mission, the descendants of the original crew decide they don't want to continue? What if they want to turn back? By that point, Earth might be 600 years away by travel time. The mission parameters were set centuries ago. The trajectory is locked in. The fuel budget doesn't allow for course changes. These people are trapped by decisions made by the dead. And there's another deeply disturbing possibility that geneticists have been quietly modeling in recent years. What if the population aboard a generation ship doesn't just stagnate? What if it regresses? I'm talking about biological regression, evolutionary pressure, acting in ways we don't anticipate. On Earth, humans are subject to natural selection pressures that favor certain traits: disease resistance, physical fitness, cognitive ability. But on a generation ship, the environment is radically different. There's no evolutionary pressure to maintain traits that were useful on Earth, but are irrelevant in space. There's no need for strong bones if you're living in low gravity or microgravity. There's no need for robust immune systems if the environment is sterile and disease vectors are limited. There's no need for high intelligence if your role in the ship's society is repetitive manual labor Frédéric Marin's research team at the University of Strasbourg ran simulations that included not just neutral genetic drift, but phenotypic effects of gene expression. That means they modeled how genetic changes actually manifest in physical traits like life expectancy, fertility, and health. What they found was chilling. If the ship's radiation shielding fails or degrades over time, cosmic rays bombard the crew with high-energy particles. This doesn't just increase cancer risk, it causes mutations in reproductive cells, mutations that get passed to the next generation. Over centuries, the cumulative mutational load can become catastrophic. Fertility drops, miscarriage rates climb, life expectancy plummets. The population begins a slow genetic collapse, and there's nothing they can do to stop it because they can't escape the radiation environment, even if the shielding holds. Even if radiation exposure is kept to acceptable levels, you still have the problem of genetic drift. In small, isolated populations, random genetic changes accumulate over time. Beneficial traits can be lost purely by chance. Harmful recessive alleles, normally kept in check by a large, diverse population, can become common. This is basic conservation biology. It's why wildlife biologists worry about endangered species with small populations. It's why zoos coordinate breeding programs to maximize genetic diversity. The same principles apply to humans on a generation ship, except the timescale is longer and the stakes are higher. If the population falls below a critical threshold, if genetic diversity is lost, the crew could experience a phenomenon called inbreeding depression. Birth defects increase, immune systems weaken, the population becomes fragile, vulnerable to any shock, and recovery becomes impossible. Let's shift gears and talk about cosmic radiation in more detail, because this is one of the most insidious threats to a generation ship. On Earth, we're protected by a magnetic field and a thick atmosphere. These shields absorb and deflect the vast majority of high-energy particles streaming from the Sun and from deep space. Astronauts on the International Space Station, even though they're in low Earth orbit, still benefit from some protection from Earth's magnetic field. But a generation ship traveling through interstellar space has no such protection. It's exposed to galactic cosmic rays, which are protons and heavy ions accelerated to near light speed by supernova explosions and other violent cosmic events. These particles carry so much energy that they can punch straight through metal hulls, through water tanks, through human tissue. When a high-energy particle strikes the human body, it doesn't just damage the cell it hits. It creates a cascade of secondary particles, a shower of fragments that radiate outward, damaging surrounding cells. If this happens in a somatic cell, a regular body cell, it can cause cancer. If it happens in a germ cell, a reproductive cell, it causes a mutation that gets passed to offspring. NASA's research on deep space radiation exposure estimates that astronauts on a 3-year Mars mission would face a significant increase in cancer risk, even with the best shielding we can currently design. Now extrapolate that to a 1,000-year journey. The cumulative radiation dose over multiple generations could be staggering. Shielding helps, but it's not a perfect solution. The most effective radiation shield is mass. You need meters of water, or rock, or metal between the crew and space, but mass is the enemy of space travel. Every kilogram you add to the ship requires more fuel to accelerate it, more structural support to hold it together, more complexity in the design. The Project Hyperion design competition, run by the Initiative for Interstellar Studies in 2025, asked teams to design habitats for a generation ship carrying 1,000 people on a 250-year journey. The winning designs used rotating habitats to simulate gravity, but even with advanced materials and optimized layouts, the shielding requirements were enormous. And remember, this was for 250 years. For a journey lasting thousands of years, the engineering challenges multiply exponentially. There's also the problem of maintenance. Radiation shielding isn't a passive system you can install and forget. Materials degrade, composite structures can delaminate, water-based shielding can develop leaks. If the outer layers of shielding are damaged by micrometeorite impacts, which are inevitable over millennia, the effectiveness drops. You'd need a crew of engineers constantly monitoring and repairing the shielding, replacing sections, redistributing mass. And if they fall behind, if maintenance lapses for even a few decades, the consequences accumulate. Radiation exposure creeps up, health problems increase, and by the time the crew realizes the damage is done, it's too late to reverse it. Now let's talk about something that doesn't get enough attention in discussions of generation ships: the psychological impact of purposelessness. Humans need meaning. We need to feel that our lives matter, that our work contributes to something worthwhile. The original crew of a generation ship has purpose. They're the pioneers, the founders, the ones who made the impossible possible. They're building the ship, launching the mission, setting the course for humanity's future. They have a role in history. But what about the people born 200 years into the mission? What's their purpose? They're not explorers. They're not pioneers. They're maintenance workers. They're cogs in a machine, performing tasks to keep a ship running so that people they'll never meet can reach a destination they'll never see. That's a recipe for existential despair. Research on long-duration confinement, from Antarctic research stations to submarine crews to prison populations, consistently shows that a sense of purpose is critical for mental health. When people feel that their work is meaningful, they can tolerate hardship, monotony, even danger. But when they feel trapped in pointless routines, psychological breakdown is almost inevitable. Depression rates skyrocket. Suicide becomes a risk. Social cohesion fractures. On a generation ship, where there's no escape, no end in sight, no possibility of a different life, the psychological toll could be unbearable. And unlike Earth, where people experiencing severe mental health crises can be hospitalized, treated, removed from the stressful environment, on a generation ship, there's nowhere to go. The environment is the problem, and it cannot be changed. There's also the issue of technological stagnation. On Earth, technology advances because of competition, because of curiosity, because thousands of researchers in different institutions are experimenting, innovating, sharing ideas. A generation ship is technologically frozen in time. The technology aboard the ship is whatever was state-of-the-art when it launched. There are no upgrades, no new discoveries being transmitted from Earth, because by the time radio signals catch up, traveling at the speed of light, they're years or decades out of date. If the ship left Earth in the year 2100, by the year 2300, Earth might have developed fusion drives, artificial gravity, advanced AI systems, none of which the generation ship can access. The crew is stuck with early 22nd century technology, trying to solve 24th century problems. It's like trying to repair a modern computer with tools from the 1950s. And here's where the situation becomes even more tragic. Imagine that generation ship, launched with the best technology humanity could muster in the year 2100, crawling through space at a fraction of light speed. 500 years into the journey, Earth develops a breakthrough. Maybe it's a functioning warp drive, or a stable wormhole generator, or simply a far more efficient propulsion system that can reach 10% light speed instead of 1%. A new ship launches, races past the old generation ship, and arrives at the destination centuries before the original crew's descendants. The generation ship becomes obsolete mid-journey. Those people spent 500 years in confinement, thousands of lives lived and died in that metal prison, and it was all for nothing. The mission they sacrificed everything for was completed by someone else. They're flying museum pieces, ghosts haunting a vessel that no longer has a purpose. This isn't science fiction speculation. This is a real problem called the interstellar weight calculation, first explored by Dr. Andrew Kennedy in a 2006 paper. He calculated the optimal launch date for an interstellar mission based on the rate of technological advancement. His conclusion was sobering. If technology improves fast enough, it's always better to wait. Launching too early means your slow ship will be overtaken by faster ships launched later. But waiting forever means you never go. There's a narrow window where launching makes sense, and predicting that window requires knowing the future trajectory of technological development, which, of course, we cannot know. From the perspective of the crew aboard that generation ship, this is psychological torture. Imagine knowing that Earth is still advancing, still innovating, and that there's a non-zero chance your entire journey is futile. Some researchers have suggested that generation ships should maintain radio contact with Earth, receiving updates, culture, news, scientific discoveries. But that creates its own nightmare. Every message from Earth would be a reminder of everything the crew is missing. They'd watch via time-delayed transmissions as Earth solves problems they still struggle with, as Earth's population enjoys freedoms and experiences impossible aboard the ship. The psychological impact could be devastating. Some mission planners have argued the opposite. Cut all contact with Earth. Let the crew develop their own culture, their own identity, free from the shadow of the homeworld. But that creates a different risk. Without external input, the population could stagnate culturally, intellectually, socially. They could forget why they're on the mission in the first place. Let's examine a specific scenario that keeps mission planners awake at night. Cascading system failures. Complex systems don't fail all at once. They fail in cascading sequences, where one failure triggers another, which triggers another until the entire system collapses. The International Space Station has experienced multiple incidents where a single component failure caused ripple effects through interconnected systems. In a 2025 study on regenerative life support systems aboard the ISS, researchers documented how the life support rack experienced a series of failures. Filter clogging led to water loop problems, which caused pump failures, which affected humidity control, which impacted sensor accuracy, which led to software errors that triggered power trips. Each failure made the next failure more likely. Engineers call this brittleness, and it's the Achilles heel of tightly integrated systems. A generation ship would be the most tightly integrated system ever built. Everything connects to everything else. The power system feeds the life support system. The life support system provides air and water to the agricultural system. The agricultural system produces food and recycles waste. The waste recycling system feeds back into life support. If any one of these systems begins to fail, the others are affected. And because the ship is a closed system, there's no margin for error, no buffer, no reserve that isn't already allocated. You can't just order more oxygen or import fresh water. What you have is all you'll ever have. NASA's research on ultra-reliable closed-loop life support estimates that to achieve the reliability needed for multi-century missions, you'd need redundancy at every level. Not just backup systems, but backups for the backups. Multiple independent life support loops, isolated from each other so that a failure in one doesn't propagate to the others. But redundancy adds mass, complexity, and maintenance burden. Every redundant system is another system that needs monitoring, repair, and eventual replacement. The more complex the ship, the more things that can go wrong, and the more expertise required to keep everything running. It's a vicious cycle. And then there's something called unknown unknowns. These are failure modes you didn't anticipate, problems that arise from the interaction of systems in ways no one predicted. The ISS, despite being one of the most intensively studied engineering projects in history, still experiences unexpected problems. Microbes eat through materials in ways not predicted by ground tests. Fluids behave differently in microgravity than they do in laboratory simulations. Electronics degrade in unexpected patterns, and the ISS has been operational for just over 2 decades, with constant resupply and support from Earth. A generation ship must function autonomously for 50 times that duration, with zero support. The probability of encountering unknown failure modes approaches certainty. Here's a specific example that illustrates the fragility of closed ecosystems. In the 1990s, scientists built Biosphere 2, a sealed ecological system in Arizona designed to test whether humans could survive in a completely closed environment. It was a 3-acre facility containing miniature ocean, rainforest, desert, and agricultural zones. 8 people sealed themselves inside for 2 years. The mission was a disaster. Oxygen levels dropped because soil microbes consumed more oxygen than plants could produce. Carbon dioxide spiked. 19 of 25 vertebrate species went extinct. Pest populations exploded. Interpersonal conflicts erupted. By the end, the crew was surviving on emergency oxygen supplies pumped in from outside. And this was on Earth in a controlled environment with a team of scientists monitoring every variable, ready to intervene. The experiment lasted 2 years, not 200. Now scale that up to a generation ship. The ecological complexity is orders of magnitude higher. You're not just supporting 8 people for 2 years, you're supporting thousands for millennia. Every species you include, every microbe, every plant, every animal becomes part of an interconnected web. Disrupt one node, and the entire web can collapse. Ecologists call this ecosystem brittleness, and it's a fundamental problem in conservation biology. Small, isolated ecosystems are inherently unstable. They lack the resilience of large, diverse ecosystems that can absorb shocks and adapt to change. Let's talk about something even more unsettling: cultural drift and mission abandonment. Over centuries, the culture aboard a generation ship would inevitably diverge from Earth's culture. Language would change, customs, values, beliefs, all would evolve in isolation. This isn't speculation, it's linguistic and anthropological fact. Isolated human populations on Earth develop distinct dialects within generations and entirely new languages within centuries. After 500 years, the crew's language might be unintelligible to Earth. Their cultural reference points, their understanding of history, their entire worldview would be shaped by life aboard the ship. Earth would become a myth, a story told by elders, increasingly abstract and distant. And here's the critical question: would they still care about the mission? The original crew had a connection to Earth. They remembered blue skies, oceans, forests, the diversity and wonder of a living planet. Their motivation to reach a new world was deeply personal. But 10 generations later, no one aboard the ship has ever seen a planet. Earth is ancient history. The destination is still centuries away. The mission itself might start to seem pointless. Why are we doing this? Why are we maintaining these systems, following these rules, sacrificing our freedom for a place we'll never reach? If enough of the crew loses faith in the mission, if social cohesion breaks down, the mission fails. They might decide to shut down non-essential systems to conserve power, abandon the agricultural zones, stop having children, let the population dwindle. The ship becomes a tomb, drifting silently through the void, a monument to a dream that died somewhere between the stars. This phenomenon is called generational mission decay, and it's been studied in the context of multi-generational projects on Earth. Cathedrals that took centuries to build, irrigation systems that required maintenance across generations. These projects succeeded only when each generation was deeply invested in the outcome, when the culture reinforced the mission's importance, when there were social structures to ensure continuity. On a generation ship, maintaining that cultural continuity is exponentially harder because the environment is so alien, so divorced from human evolutionary context. Consider also the issue of information preservation. The ship's crew needs access to vast libraries of knowledge, engineering manuals, medical texts, agricultural guides, cultural archives. This information must be preserved for centuries, readable by people whose language and technology might have drifted from the original. Digital storage degrades, hard drives fail, optical media deteriorates. Even if you use multiple redundant storage systems, you face the problem of format obsolescence. Will computers 500 years from now be able to read file formats from 500 years earlier? On Earth, we struggle to read digital files from the 1980s. Now imagine that problem amplified across centuries with no ability to download updated software or consult with Earth-based experts. Some proposals suggest encoding critical information in physical form, etched metal plates, printed books, microfilm, but physical media has its own problems. Books decay, especially in controlled atmospheres where humidity and temperature fluctuate. Metals corrode, and physical libraries require space, a precious commodity on a generation ship. There's also the question of who decides what information is essential. Do you bring literature, art, music? Do you preserve the history of Earth's civilizations, or do you focus purely on technical manuals? Every byte of data, every kilogram of books is a choice, and choices made at the beginning of the mission bind all future generations. Now let's confront one of the most disturbing possibilities, one that ethical philosophers and mission designers debate behind closed doors but rarely discuss publicly: authoritarian control. A generation ship, by its very nature, requires strict social organization. Resources must be carefully managed, population must be controlled, everyone must perform their assigned role. Deviation from the plan threatens the entire mission. This creates an environment where authoritarian governance is not just likely, it might be necessary for survival. Think about the power dynamics. The original mission designers, the people who built the ship and selected the crew, they established the rules, they create the governance structure, the social hierarchy, the laws that will govern thousands of people for thousands of years. But they won't be around to see how those systems evolve. What's to stop those systems from becoming oppressive? What's to stop a charismatic leader, born 5 generations into the mission, from seizing control and establishing a dictatorship? There's no external authority to appeal to, no international community to intervene, no possibility of revolution, because where would the revolutionaries go? You can't escape a generation ship. You either accept the social order or you face punishment, exile to isolated sections of the ship, or worse. Historical parallels are deeply troubling. Isolated human populations on Earth, cut off from external oversight, have repeatedly descended into tyranny. Remote colonies, prison camps, cult compounds all show what happens when a small group of people has absolute power over a captive population. The Stanford prison experiment, though controversial in its methodology, demonstrated how quickly ordinary people can abuse authority when placed in positions of power over others. On a generation ship, those in control have ultimate power. They control life support, food distribution, access to medical care, reproductive rights. If they become corrupt, if they prioritize their own interests over the mission, there's no mechanism to remove them without risking civil war, which on a generation ship would be catastrophic. A violent conflict in a pressurized vessel surrounded by vacuum could rupture critical systems and kill everyone. Some mission designers have proposed democratic governance with regular elections, checks and balances, constitutional protections for individual rights. But democracy requires an informed, engaged population. It requires free exchange of ideas, access to information, the ability to organize and protest. Can these freedoms coexist with the rigid discipline required for survival on a generation ship? What happens when the elected government makes a decision that threatens the mission? What if a majority votes to change course, to abandon the mission, to redistribute resources in ways that jeopardize long-term survival? Do you override democracy to save the mission? And if you do, what does that make you? These are not abstract ethical dilemmas. These are practical governance challenges that would arise within the first few generations. And there's no rulebook, no precedent, no tested model for how to govern a multi-generational space mission. We'd be making it up as we go, and the consequences of failure are total extinction of the crew. Let's shift to another nightmare scenario: epidemic disease. Despite strict quarantine protocols, despite medical screening, microorganisms are inevitable aboard a generation ship. Humans carry trillions of bacteria and viruses. Some are beneficial, part of our microbiome. Others are opportunistic pathogens, kept in check by our immune systems. In the closed environment of a generation ship, these microorganisms evolve. They adapt to the artificial environment. They exchange genetic material, and occasionally they become dangerous. On Earth, when a new infectious disease emerges, we have global health infrastructure to respond. Epidemiologists trace outbreaks, pharmaceutical companies develop treatments, vaccines are manufactured and distributed. A generation ship has none of this. The crew's medical facilities are limited. They have whatever supplies they brought from Earth, plus whatever they can synthesize aboard the ship. If a novel pathogen emerges, something the crew's immune systems have never encountered, it could sweep through the population like wildfire. In a confined environment, disease transmission is incredibly efficient. Everyone breathes the same air. Water is recycled. Surfaces are shared. Social distancing is impossible when you're living in a metal cylinder with a few thousand other people. The Black Death killed a third of Europe's population in the 14th century. The Spanish flu of 1918 killed 50 million people worldwide. These pandemics occurred in open populations with escape routes, rural areas where people could isolate. On a generation ship, there's nowhere to run. If a highly contagious, lethal disease emerges, it could kill half the crew before doctors even understand what they're dealing with. And if the population drops below the minimum viable threshold, genetic diversity collapses and the mission fails. There's also the psychological impact of epidemic disease. During the COVID-19 pandemic on Earth, even with modern medicine, with hospitals, with the knowledge that the crisis would eventually end, societies experience profound psychological trauma, anxiety, depression, social isolation, conspiracy theories, breakdowns in trust. Now imagine that scenario on a generation ship where resources are scarce, where there's no external help coming, where the knowledge that you're trapped with a deadly pathogen creates existential terror. The social fabric could tear apart. Panic could lead to violence. People might barricade themselves in sections of the ship, refusing to cooperate with medical authorities, hoarding resources, fracturing the crew into hostile factions. Once that happens, even if the disease is eventually controlled, the social damage might be irreparable. Now let's discuss something that sounds almost mundane, but is actually critical: supply chain failure. On Earth, we take for granted that if something breaks, we can get a replacement. A part fails, we order a new one. A tool wears out, we buy another. This works because Earth has a global industrial supply chain, billions of people producing and distributing goods. A generation ship has no supply chain. It has storage, whatever spare parts, tools, raw materials the designers thought to include, that's all there is. Forever. Studies on long-duration space missions have shown that predicting what will break and when is extraordinarily difficult. Components fail in unexpected ways, tools wear out faster or slower than predicted, materials behave differently in space than they do on Earth. The ISS regularly receives resupply missions, bringing not just food and water but replacement parts, new tools, updated equipment. A generation ship gets one loadout at the beginning and then nothing. Imagine you're the chief engineer 400 years into the mission. A critical pump fails. You check the inventory, no spares. The last spare was used a century ago. Can you fabricate a replacement? Do you have raw materials? Do you have the manufacturing equipment? Do you have the technical drawings? Do you have the expertise? Maybe the original designers included a machine shop, 3D printers capable of manufacturing precision parts. But those machines also break down. They require maintenance, calibration, replacement components. And if the knowledge of how to operate them has been lost, if the training programs have degraded over generations, you might have a functional machine shop, but no one who knows how to use it. This problem compounds over time. Every repair consumes resources. Every manufactured part uses raw materials that can't be replaced. The ship's industrial capacity slowly degrades. Maybe it takes 500 years, maybe 1,000, but eventually you reach a point where you can no longer manufacture critical components. When that happens, systems begin to fail permanently. Life support capacity drops. Agricultural production declines. The crew faces a slow, inevitable collapse, and there's nothing they can do to stop it. Let's talk about artificial gravity, or rather, the lack of it. Most generation ship designs include rotating sections to simulate gravity through centrifugal force. This is necessary because long-term exposure to microgravity causes severe health problems, bone density loss, muscle atrophy, cardiovascular degeneration, vision problems, immune system dysfunction. Astronauts on the ISS experience these effects after just 6 months. Over a lifetime, over multiple generations, the health consequences would be catastrophic if the crew lived in zero gravity. But rotating habitats introduce their own nightmares. The engineering is complex. You need massive rotating structures, kilometers in diameter, to minimize the Coriolis effect, which causes disorientation and nausea. The rotation must be perfectly balanced. Any asymmetry, any uneven distribution of mass creates wobble and stress on the structure. Over centuries, as people move, as cargo is relocated, as sections of the ship are modified, maintaining balance becomes increasingly difficult, and the bearings that allow the habitat to rotate, these are mechanical systems subject to wear. They require lubrication, maintenance, eventual replacement. If the rotation system fails, if the habitat stops spinning, everyone suddenly experiences zero gravity. The health consequences would be immediate and severe. There's also a psychological dimension to rotating habitats. The Coriolis effect, even when minimized, still exists. Moving in a rotating reference frame feels wrong. When you throw a ball, it curves. When you pour water, it spirals. Your inner ear, which controls balance, receives conflicting signals. Some people adapt. Others experience chronic motion sickness, vertigo, spatial disorientation. On Earth, if you get seasick, you get off the boat. On a generation ship, you're stuck with that sensation for life. Studies of people living on rotating space station mock-ups show that even after months, some individuals never fully adapt. They exist in a constant state of low-grade nausea, which impacts appetite, sleep, cognitive function, and psychological well-being. Let's examine the agricultural systems in more detail, because this is where the margin for error is thinnest. A generation ship must grow all its own food. There's no importing grain, no fishing, no hunting. Every calorie must come from carefully managed crops and possibly small-scale animal husbandry. The crew needs a balanced diet: carbohydrates, proteins, fats, vitamins, minerals. This requires multiple crop species, each with its own growing requirements, each vulnerable to its own diseases and pests. On Earth, agriculture is sustained by vast ecosystems, pollinators like bees and butterflies, soil microorganisms that fix nitrogen and break down organic matter, natural pest predators, rain cycles that provide water, seasonal variations that reset ecosystems. A generation ship has none of this. Pollination must be done manually or by carefully maintained insect populations. Soil must be artificially enriched with nutrients recycled from waste. Water must be precisely distributed. Light must come from LEDs powered by the ship's electrical systems. Temperature and humidity must be controlled. It's hydroponics and aeroponics on a massive scale, and every variable must be monitored constantly. The most terrifying scenario is crop failure. It could start with something small. A fungal pathogen that somehow survived decontamination before launch, lying dormant for decades, suddenly proliferates in the humid environment of the agricultural pods, or a pest species, maybe something as simple as mites or aphids, finds conditions ideal for explosive population growth, or an error in the environmental control system causes temperatures to spike for just a few days, long enough to stress the crops and reduce yields. In a diverse planetary-scale ecosystem, local failures are absorbed. One region's crop failure is compensated by another region's surplus. On a generation ship, there is no other region. The agricultural zones are all you have. If yields drop by 20%, food rations drop by 20%. If a critical crop fails entirely, the crew faces starvation. Food security researchers have calculated the minimum agricultural capacity needed to sustain various population sizes on generation ships. The numbers are sobering. For a crew of 1,000 people, you need approximately 2 to 3 hectares of growing space, depending on crop types and yields. That's assuming optimal conditions, no crop failures, perfect efficiency. In reality, you'd need significant surplus capacity, buffer zones, and multiple redundant growing areas in case one section fails. But every square meter of agricultural space requires structural support, lighting, environmental control, water distribution. It's heavy, it's complex, and it's a single point of failure for the entire mission. There's also the problem of dietary monotony. On Earth, humans eat thousands of different plant and animal species. This diversity isn't just about pleasure, it's about nutrition and psychological well-being. On a generation ship, the crew might have access to maybe 10 or 20 crop species: wheat, rice, soybeans, potatoes, leafy greens, a few fruits, day after day, year after year, generation after generation, eating the same meals. Studies of Antarctic research stations and other isolated facilities show that dietary monotony contributes significantly to psychological stress. People crave variety, novelty, comfort foods associated with home. On a generation ship, those comforts don't exist. You eat what the agricultural system produces, nothing more. For some people, this is a minor inconvenience. For others, it's a form of psychological torture that compounds over time. And let's not forget food safety. On Earth, food contamination causes illness, sometimes death, but society continues. On a generation ship, a contamination event could be catastrophic. Imagine a toxin-producing bacteria somehow infiltrates the water recycling system that irrigates the crops. The contamination isn't detected immediately because monitoring systems have degraded or personnel are undertrained. The toxin accumulates in the food supply. People start getting sick. By the time doctors identify the problem, a significant portion of the crew is affected. Some die. Others suffer permanent organ damage. The contaminated crops must be destroyed, but the contamination has spread throughout the agricultural system. Decontamination requires shutting down food production for weeks or months. The crew survives on emergency rations, but those rations are finite. Panic sets in, social order breaks down. Even if the contamination is eventually controlled, the mission has been dealt a blow it may not recover from. Let's talk about something that mission planners rarely acknowledge publicly: the problem of reproductive control. This is one of the most ethically fraught aspects of generation ship design. The population must remain stable. If it grows too large, resources are depleted. If it shrinks too small, genetic diversity collapses. This means the crew's reproductive choices cannot be left to individual freedom. There must be some form of population control. How do you implement this? Do you assign reproductive quotas? Does a central authority decide who can have children and when? Do you require contraception and only allow pregnancy by permit? These policies sound dystopian, and they are, but without them, the mission fails. If people have as many children as they want, population could double in a generation. Food production can't scale that fast. Life support can't expand to accommodate more people. The ship wasn't designed for population growth, so either you control reproduction or you face resource collapse and mass starvation. But reproductive control has profound psychological and ethical consequences. On Earth, the right to have children is considered fundamental. It's enshrined in human rights declarations. People make deeply personal decisions about when and whether to become parents. On a generation ship, those decisions are made by committee, by algorithm, by necessity. Imagine being told you cannot have a child because the population quota has been met, or being told you must have a child because the population needs genetic diversity from your lineage, or worse, imagine being told your child cannot survive because of genetic defects, because limited medical resources must be reserved for healthier individuals. These are not hypothetical dilemmas. These are decisions the crew would face regularly, and they would tear the social fabric apart. Some mission designs propose selecting crew members who are psychologically suited to this reality, people who can accept reproductive restrictions for the greater good. But personality traits change over generations. The descendants of the original crew might not share their ancestors' commitment to the mission. Rebellion becomes likely. And if rebellions over reproductive rights turn violent, if factions form around these issues, the mission implodes. There's another issue related to reproduction: genetic engineering. At the planning stages on Earth, mission designers would have access to advanced genetic technologies. They could screen embryos for genetic diseases, select for traits that might be advantageous in space, maybe even edit genomes to enhance radiation resistance or bone density. This raises obvious ethical questions, but let's assume those debates are settled and some level of genetic intervention is deemed acceptable. The real problem emerges later. What if, 300 years into the mission, a genetic disease appears that wasn't predicted? A recessive disorder that only manifests when two rare alleles combine. The crew's geneticists would want to use gene therapy to correct it, but their knowledge is limited to whatever was known when the ship launched, plus whatever they've been able to learn through experimentation. They might lack the tools, the understanding, the techniques to safely intervene. A botched genetic intervention could introduce new problems, creating a cascade of genetic instability across subsequent generations. Let's discuss interstellar navigation, because even this seemingly technical challenge has nightmare dimensions. A generation ship isn't just traveling through empty space. It's traveling through a cosmic shooting gallery. Micrometeorites, dust grains, rogue asteroids all pose collision risks. At high velocities, even a grain of sand carries enormous kinetic energy. Impact with a particle the size of a pebble could punch through the hull, causing explosive decompression in that section. Larger objects could destroy entire modules. Detection and avoidance systems are critical. The ship needs radar, LiDAR, telescopes constantly scanning the space ahead, identifying potential hazards, calculating trajectories, and making course corrections. But these systems are only as good as their maintenance. Sensors degrade, Software needs updates, the crew needs training to interpret the data and respond appropriately. Over centuries, if institutional knowledge decays, if the crews responsible for navigation become complacent or undertrained, the ship becomes vulnerable. One misdetection, one calculation error, and the mission ends in an instant, the ship vaporized by an impact no one saw coming. There's also the problem of navigation accuracy. Even small errors in trajectory compound over interstellar distances. If the ship's course is off by a fraction of a degree, over thousands of years, it could miss the target star system entirely. Imagine the horror of the crew realizing, after centuries of travel, that they're going to miss their destination. They've spent their entire existence pursuing a goal they will never reach. The mission is a failure, and there's nothing they can do. They don't have fuel to correct course. They don't have time to recalculate and reach an alternative destination. They're committed to a trajectory that leads nowhere. The psychological impact would be annihilating. Despair would consume the crew. Why continue? Why maintain the ship? Why have children? Why follow the rules when the mission is already lost? And even if navigation is perfect, there's no guarantee the destination is habitable. When the mission launched, Earth's telescopes identified a potentially habitable exoplanet. Spectroscopy showed signs of water vapor, oxygen, perhaps even biosignatures. But those observations were made from light years away, using instruments that can only detect gross planetary characteristics. The crew won't know the ground truth until they arrive. What if the planet's atmosphere is toxic? What if the gravity is too strong for humans to survive long term? What if the surface is dominated by hostile extremophiles, alien microorganisms that attack human biology in ways we can't predict or defend against? The crew would have no choice but to stay in orbit, trying to survive in a deteriorating ship, unable to land, unable to return to Earth, trapped in a cosmic dead end. Some mission proposals include robotic scouts sent ahead of the generation ship, arriving decades earlier to assess conditions and relay information back. But this assumes the scouts function perfectly, that their data transmission systems work, that the generation ship receives and correctly interprets the data. Any failure in this chain and the crew arrives blind. Now let's confront the radiation problem in its full horror, because this is perhaps the single most intractable challenge. Space is flooded with ionizing radiation, cosmic rays, solar particle events, galactic cosmic radiation. On Earth, we're protected by a magnetic field and a thick atmosphere. In space, there's no protection except whatever shielding the ship provides. And here's the nightmare. Effective radiation shielding requires mass, lots of mass. The most practical shielding material is water, hydrogen-rich polymers, or simply thick layers of metal and rock. To provide Earth-like protection, you'd need shielding several meters thick surrounding the entire habitable volume. For a ship designed to carry thousands of people, we're talking about millions of tons of shielding material. This isn't just difficult to launch from Earth, it's functionally impossible with any propulsion technology we can currently envision. Every kilogram of shielding requires exponentially more fuel to accelerate and decelerate. The mass budget explodes beyond feasibility, so mission designers compromise. They design ships with minimal shielding, accepting that the crew will be exposed to elevated radiation levels. They calculate acceptable doses, estimate cancer risks, plan for medical interventions. But here's what the sanitized mission reports don't emphasize. The crew will be dying of cancer at rates far higher than Earth populations. Childhood leukemia, brain tumors, reproductive cancers. The medical facilities aboard the ship will be overwhelmed with oncology cases, and these aren't quick deaths. Cancer is a long, painful deterioration, watching your friends, your family, your children waste away from radiation-induced malignancies, generation after generation, knowing it's an inevitable consequence of the mission. This is psychological torture on a civilization-wide scale. There's also acute radiation exposure from solar particle events. The sun occasionally produces massive eruptions, coronal mass ejections that flood space with high-energy protons. On Earth, these create beautiful auroras. In space, they're lethal. An unshielded astronaut caught in a major solar particle event would receive a fatal dose within hours. Generation would need storm shelters, heavily shielded areas where the crew can retreat during radiation events. But these shelters would be cramped, and the crew might need to remain there for days while the radiation subsides. Now imagine a solar particle event coinciding with another crisis, a fire, a medical emergency, a structural failure. The crew is trapped in the storm shelter, unable to respond, while disaster unfolds in other parts of the ship. And then there's cosmic ray exposure, which is even worse. Cosmic rays are high-energy particles, often atomic nuclei traveling at relativistic speeds, produced by supernovae and other violent cosmic phenomena. When a cosmic ray passes through human tissue, it creates a track of ionization, damaging DNA and cellular structures. Over a lifetime of exposure, the cumulative damage is significant. But here's the truly insidious part. Cosmic rays also damage electronics. They cause bit flips in computer memory, corrupting data. They degrade solar panels and electronic components. Shielding electronics requires additional mass and design complexity. Over centuries, cosmic ray damage to the ship's computer systems could cause cascading failures, navigation errors, life support malfunctions, data loss in critical archives. Some researchers have proposed using magnetic shielding, creating an artificial magnetosphere around the ship to deflect charged particles. This sounds elegant, but the engineering is staggering. You'd need superconducting magnets generating enormous magnetic fields, consuming massive amounts of power continuously for centuries. The magnetic fields themselves could pose health risks. Long-term exposure to strong magnetic fields affects human physiology in ways we don't fully understand. And if the magnetic shielding system fails, if the superconducting magnets quench or the power supply is disrupted, the crew suddenly faces full radiation exposure with no warning. Let's talk about something even more existentially disturbing: the problem of meaning. Human beings need purpose. We need to feel that our lives matter, that our efforts contribute to something larger than ourselves. On Earth, people find meaning in countless ways: relationships, careers, creative pursuits, spiritual practices, contributing to their communities. On a generation ship, the range of possible meanings is constrained. The mission is the meaning. Everything exists in service to reaching the destination. But for the middle generations, the ones born and dying between the stars, the mission is abstract. They'll never see Earth. They'll never reach the destination. Their entire existence is lived in transit, in a metal cylinder, performing repetitive tasks to maintain systems they didn't choose to board. Psychologists studying extreme isolation, Antarctic winter-over crews, submarine personnel, astronauts on long-duration missions have documented a phenomenon called third-quarter syndrome. Around the midpoint of a long mission, when the beginning is distant and the end is still far away, morale crashes. People become depressed, irritable, withdrawn. Conflicts escalate, performance declines. This happens on missions lasting months. Now scale that to centuries. Imagine being born into the 10th generation of a 20-generation mission. Your great-great-great-grandparents left Earth. Your great-great-great-grandchildren might reach the destination. But you're living and dying in the middle, and the only meaning available to you is maintaining systems so that people you'll never meet can complete a mission you'll never see fulfilled. Some people might find nobility in this sacrifice. Others would find it unbearable. Depression, nihilism, existential despair. These wouldn't be occasional psychological issues. They'd be endemic to the population. and there's no escape. You can't take a vacation, can't change careers, can't move to a different city. Your entire world is a few hundred meters long. You see the same people every day, you eat the same food, you perform the same tasks. Day after day, year after year until you die. For some people, that existence would be a form of hell. Suicide rates would likely be high. Mission planners would need psychological support systems, therapists, psychiatric medications, intervention protocols, but mental health resources are finite. If depression and suicidal ideation become widespread, if the psychological support infrastructure is overwhelmed, the social fabric starts to tear. And suicide on a generation ship isn't just a personal tragedy, it's a loss of genetic diversity, a loss of skills and knowledge, a drain on morale that affects everyone who remains. There's also the question of cultural preservation versus cultural evolution. The original mission designers would want to preserve Earth's cultural heritage, literature, music, art, history, philosophy. They'd include vast digital archives, perhaps even physical libraries. But culture isn't static, it evolves. And in the isolated environment of a generation ship, culture would evolve in strange directions, diverging from Earth in ways impossible to predict. Language would change. New belief systems might emerge. Social structures would adapt to the unique environment of the ship. Some anthropologists have speculated that generation ship cultures might become profoundly alien to Earth cultures. After several centuries of isolation, the crew might develop worldviews, values, and social practices that Earthborn humans would find incomprehensible or disturbing. Maybe they'd develop religious beliefs centered on the ship itself, worshipping the vessel as a living deity. Maybe they'd reject the mission entirely, viewing Earth and the destination as mythical places, focusing instead on the ship as their true and only home. Maybe they'd fragment into competing subcultures, each occupying different sections of the ship, developing distinct languages and customs, potentially hostile to each other. This cultural drift poses a serious risk to mission success. If the crew's culture evolves away from the original mission parameters, they might make decisions that jeopardize the mission. They might modify the ship in ways that seem sensible from their perspective, but that violate fundamental design principles. They might lose technical knowledge, allowing critical systems to fail because the cultural importance of maintaining them has been forgotten. Anthropologists call this cultural forgetting, and it's happened repeatedly in Earth's history. Island populations that lost seafaring knowledge, civilizations that abandoned technologies their ancestors mastered. On a generation ship, cultural forgetting could be fatal. Let's examine the arrival scenario. Because even if everything goes right for centuries, the final phase of the mission is extraordinarily dangerous. As the ship approaches the destination star system, it must decelerate. This requires either carrying enough fuel for a deceleration burn, which means the ship must have been much more massive at launch, or using alternative methods like magnetic sails that interact with the destination star's solar wind, or even more speculative technologies like beam-powered deceleration, where lasers from the destination system slow the ship. All of these methods have problems. If the ship is decelerating, everyone aboard experiences acceleration forces, even at relatively gentle deceleration, say 1/10 of a g, sustained over years. The structural stresses on the ship are immense. Components that have been in microgravity or gentle rotation for centuries suddenly experience sustained force in a new direction. Structures could fail, equipment could shift and rupture, people could be injured, and the crew living through deceleration would experience profound physiological effects. If they've lived their entire lives in microgravity or low gravity, their bodies aren't adapted to sustained acceleration. They'd experience what astronauts call orthostatic intolerance, a difficulty standing, blood pooling in the legs, cardiovascular stress. Some might not survive the transition. And then there's the question of what to do when they arrive. The crew has been living aboard the ship for centuries. It's the only home they've known. Now they're expected to abandon it, descend to a planet's surface, to live under an open sky with weather and ecosystems and gravity that might be similar to Earth but isn't identical. For many, this would be terrifying. Agoraphobia, fear of open spaces, could be widespread among people who've only ever known enclosed metal corridors. The psychological adjustment would be immense. And what if the planet is already inhabited? Not by intelligent life necessarily, but by microbial ecosystems. The crew lands, begins establishing habitats, growing crops. But the planet's microorganisms are alien. They didn't evolve with Earth life. They have different biochemistry, different survival strategies. Some might be harmless, unable to interact with human biology. Others might be catastrophically dangerous. Imagine bacteria that can metabolize human tissue, or fungi that colonize human lungs, or viruses that can hijack human cells despite being of alien origin. The crew would have no immunity, no evolutionary defenses against these organisms. The history of human exploration is filled with examples of disease devastation when isolated populations meet. European diseases decimated indigenous American populations who had no immunity. The crew of a generation ship arriving at an inhabited exoplanet could face the same fate in reverse. An alien pathogen sweeps through the population. Medical facilities are overwhelmed. There are no hospitals, no pharmaceutical industries, no research institutions capable of developing treatments. The crew that survived centuries of space travel dies within months of landing. Even if the planet is sterile, colonization presents staggering challenges. The crew needs to build habitats, establish agriculture, create industrial infrastructure, all while living in an environment that might be subtly hostile. Maybe the gravity is 15% higher than Earth, causing long-term cardiovascular stress. Maybe the atmosphere has trace gases that are toxic over time. Maybe the soil lacks essential nutrients or contains heavy metals that accumulate in crops. The crew would be conducting an experiment in survival on a planetary scale with no backup and no way home. Let's talk about the psychological impact of arrival itself. For centuries, the mission has been oriented toward a single goal, reaching the destination. Entire cultures have been built around this purpose. Moral authority derives from serving the mission. Social structures exist to support the journey. Then suddenly, they arrive. The mission, in its original conception, is complete. Now what? This psychological transition could be as traumatic as any physical challenge. Societies need purpose, direction, shared goals. Once the ship reaches its destination, what holds the society together? Some crew members might want to establish a planetary colony. Others might prefer to remain aboard the ship, to continue living in the environment they know. This could create a schism, those who land versus those who stay, each group viewing the other as betraying the mission or betraying the ship. If the population splits, both groups become smaller, less genetically diverse, more vulnerable to all the cascading failure scenarios we've already discussed. And here's a particularly dark possibility. What if the landing fails? The crew attempts to establish a surface habitat, but something goes wrong. Maybe the habitat fails structurally. Maybe resource extraction is more difficult than anticipated. Maybe hostile environmental conditions, radiation, storms, seismic activity make the surface unlivable. The landing party tries to return to the ship, but the ship's systems have degraded during the landing attempt. Or the ship's crew, having decided to move on to another star system or return to space, refuses to allow the landing party back aboard. The landing party is stranded on a hostile planet, slowly dying, while the ship they came on disappears into space. Let's examine another failure mode that's rarely discussed: the breakdown of the scientific method. A generation ship requires continuous scientific and technical knowledge. Engineers must understand physics, chemistry, materials science. Doctors must understand biology and medicine. Agriculturalists must understand botany and ecology. This knowledge can't just be stored in archives. It must be actively practiced, taught, tested, and transmitted across generations. But maintaining scientific rigor over centuries, in isolation with limited resources, is extraordinarily difficult. Science on Earth is a collective enterprise, with peer review, replication studies, international collaboration, access to vast databases and experimental facilities. A generation ship has none of this. The crew's scientists work in isolation, with limited equipment, communicating only with each other. Errors can creep in. Misconceptions can become entrenched. Without external validation, without the correcting mechanism of a global scientific community, the crew's understanding of science could drift into pseudoscience or cargo cult science, performing rituals that look like science but lack the underlying understanding. Historical parallels are concerning. Medieval Europe preserved some ancient scientific texts but lost the methodology that produced them, leading to centuries of stagnation. The crew of a generation ship could experience similar regression. They might retain technical manuals explaining how to operate systems, but lose the deeper understanding of why those systems work. They become technicians following scripts, not scientists who can innovate and solve novel problems. When an unexpected challenge arises, something not covered in the manuals, they lack the intellectual tools to respond. The mission fails not because of equipment malfunction, but because of intellectual atrophy. There's also the problem of educational degradation. On Earth, we have specialized educational institutions, universities, research laboratories, professional training programs. These institutions take decades to develop and require enormous resources. A generation ship has limited space, limited personnel, limited resources. Education must be efficient, focused on mission-critical skills, but this narrow focus creates vulnerability. If education becomes too specialized, too focused on maintaining existing systems, the crew loses the ability to think creatively, to innovate, to solve problems that the original designers didn't anticipate. And over generations, if educational quality declines, if teachers are poorly trained or unmotivated, if students don't see value in learning, the entire intellectual foundation of the mission erodes. Children grow up with less knowledge than their parents. Technical competence declines. Literacy rates might drop. Mathematical understanding deteriorates. The crew enters a slow intellectual descent, and by the time anyone realizes what's happening, it may be too late to reverse. Let's discuss the problem of mission memory. The original crew knows why they're on the ship. They volunteered, or their parents volunteered, for an interstellar colonization mission. They understand the risks, the purpose, the importance of reaching the destination. But their children, grandchildren, great-grandchildren, what do they understand? They were born into this situation. They didn't choose it. The mission is something they've been told about, not something they personally committed to. As generations pass, the mission becomes mythology. Earth becomes a legend, a place their ancestors came from, but that no one alive has seen. The destination becomes an abstract concept, a place they're supposed to reach, but that no one can verify exists. Why should they believe the stories? Why should they sacrifice their comfort, their freedom, their lives, for a mission they didn't choose, to reach a place that might not exist, to fulfill a promise made by ancestors who died centuries ago? This creates a profound legitimacy crisis. The authority structures aboard the ship derive their power from the mission. We must enforce these rules, ration these resources, restrict these freedoms, because the mission requires it. But if the crew stops believing in the mission, that authority collapses. You get resistance, rebellion, a refusal to cooperate with mission directives, and once that happens, maintaining the ship becomes nearly impossible. If people won't repair systems, won't follow safety protocols, won't accept resource rationing, the ship slides toward chaos and failure. Some mission designs include reminder systems, the regular ceremonies, educational programs, cultural practices designed to keep the mission at the forefront of collective consciousness. But these can feel manipulative, like propaganda, and over time, they lose effectiveness. Rituals become empty performances. The words are recited, but their meaning fades. The crew goes through the motions while internally disconnecting from the mission's purpose. There's an even darker possibility. What if the crew learns something that undermines the mission? Imagine, centuries into the journey, the crew's scientists make a discovery. Maybe they develop better telescopes, observe the destination star system more carefully, and realize the target planet is definitely uninhabitable. Or maybe they intercept a signal from Earth, a message sent centuries after their launch, traveling faster than the ship, informing them that Earth has developed faster than light travel and has already colonized the destination planet, making the generation ship obsolete. Or perhaps they simply conclude, based on their centuries of experience living aboard the ship, that the entire concept of generation ships is flawed, that humanity should never have attempted this, that continuing the mission is pointless suffering. What do they do with that information? Do the leaders suppress it, knowing that revealing it would destroy morale and doom the mission? Do they tell the crew, risking mass despair and social collapse? There's no right answer, only terrible choices with catastrophic consequences either way. Let's talk about the children. Throughout this analysis, we've discussed the crew as an abstract entity, but generation ships are populated by individuals, people with names, personalities, hopes, fears, dreams, and most significantly, children. Every generation of the journey includes children who are born aboard the ship, who grow up knowing nothing else, who will spend their entire lives in this environment. What kind of childhood can you have on a generation ship? On Earth, children need space to run, to play, to explore. They need social interaction with peers, exposure to diverse experiences, the freedom to make mistakes and learn. On a generation ship, space is limited. Every square meter is dedicated to life support, agriculture, living quarters, or industrial facilities. There might not be parks, playgrounds, or open spaces for children. They grow up in cramped quarters, under constant surveillance because safety is critical, with every aspect of their lives regulated by necessity. Child psychologists have studied children growing up in extreme environments, submarines, Antarctic stations, remote military bases. Even in these temporary situations lasting months, children show signs of stress, developmental delays, behavioral problems. Now imagine that stress sustained for an entire childhood with no alternative, no escape, no hope of change. Some children would adapt, others would suffer profound psychological damage, and there's no child protective services, no alternative caregivers, no fostering system. If a child is being abused or neglected, intervention options are extremely limited in a small, closed society where everyone knows everyone else and social relationships are fragile. There's also the question of education and opportunity for children born on the ship. On Earth, children grow up imagining different futures: astronaut, doctor, artist, entrepreneur, explorer. They have agency, choice, the possibility of shaping their own destinies. On a generation ship, career options are limited to whatever roles the ship requires: engineer, technician, farmer, doctor, teacher, administrator. Your career isn't chosen based on passion or interest, it's assigned based on aptitude and need. The ship requires 3 new hydraulic engineers this generation, so the 3 children who test highest in mechanical reasoning become hydraulic engineers. whether they want to or not. This creates a form of soft coercion that becomes harder over generations. Children born into dynasties of engineers might have no choice but to become engineers themselves because the knowledge is too specialized to train outsiders and the mission needs continuity. Social mobility becomes impossible. You're born into a role, and that role defines your entire existence. For some, this provides security and purpose. For others, it's a cage. They dream of being something else, doing something else, but the mission's needs override individual desires. The psychological toll of thwarted ambition, of being forced into a life you didn't choose, compounds across the population. And what about children born with disabilities? On Earth, societies struggle to provide adequate support for people with physical or cognitive disabilities, but at least the resources exist. Specialized schools, therapeutic interventions, assistive technologies, social support systems. On a generation ship, resources are scarce. A child born with severe disabilities requires disproportionate medical and social resources. The ship's limited medical facilities, already stretched managing radiation-induced cancers and other health crises, might be unable to provide adequate care. Worse, the cold calculus of resource management might lead to horrifying decisions that severely disabled children represent an unsustainable burden, that scarce resources must be allocated to healthier individuals who can contribute to the mission. This veers into eugenics territory, one of the darkest chapters of human history. But on a generation ship, where survival margins are razor thin, where every calorie and every medical resource is precious, these utilitarian calculations become grimly practical. Mission designers wouldn't plan for this explicitly, but the situations would arise and crew members would have to make decisions that would haunt them. Do we use limited resources to keep alive a child with severe cerebral palsy, knowing they'll never be able to contribute to ship operations? Or do we allocate those resources to treating a radiation-exposed engineer whose skills are critical? There's no moral high ground here, only terrible choices born of impossible constraints. Let's examine the problem of violence and crime. Human societies have always struggled with violence. Interpersonal conflicts, domestic abuse, assault, murder. On Earth, societies have developed systems to manage this. Police, courts, prisons, rehabilitation programs. These systems are imperfect, often unjust, but they provide mechanisms for addressing violence without total social breakdown. On a generation ship, with a small population and limited space, traditional justice systems are nearly impossible to implement. Imagine a murder aboard the ship. Someone driven by rage, jealousy, mental illness, or ideological extremism kills another crew member. What do? There's no prison system. The ship can't afford to dedicate space and resources to confining people long-term. Do you execute the murderer? That eliminates a threat but reduces genetic diversity and sets a precedent that might be abused. Do you rehabilitate them and reintegrate them into the community? But in a population of a few hundred or a few thousand, everyone knows what happened. The victim's family and friends must live and work alongside the murderer every day. The psychological strain would be unbearable. If you're finding these nightmare scenarios as fascinating as they are terrifying, make sure to subscribe to the channel. We're just getting started, and the problems only get darker from here. Some mission designs propose exile as punishment for serious crimes, putting the offender in a small escape pod or isolated section of the ship, cutting them off from the community. But this is essentially a death sentence, slow and cruel. And it raises questions. At what point does punishment become torture? When does necessity justify inhumane treatment? Violence prevention becomes critical, which means constant surveillance and social control. The ship might employ extensive monitoring systems, Cameras, microphones, behavioral analysis algorithms, psychological profiling. Privacy becomes a luxury the mission can't afford. Everyone is watched always because the stakes are too high, but constant surveillance has profound psychological effects. People feel oppressed, anxious, unable to relax or express themselves freely. Trust erodes, paranoia spreads. The society becomes authoritarian, not out of malice, but out of desperate necessity. And authoritarian societies are fragile. They depend on coercion, which breeds resentment, which eventually explodes into rebellion. Let's talk about something even more disturbing, the possibility of factional warfare. In a small, closed society under extreme stress, with no external outlet for tensions, factions can form around any number of fault lines, ideological differences, resource disputes, ethnic or cultural divisions, religious schisms, even simple personality conflicts that metastasize over generations. Once factions form and tensions escalate, violence becomes possible. Now imagine civil conflict aboard a generation ship. Two factions, each controlling different sections of the ship, fighting for dominance. This isn't warfare on a planetary scale, it's warfare in an enclosed environment where everyone is dependent on the same life support systems. A faction trying to gain advantage might sabotage the other faction's water supply, or cut power to their section, or compromise atmospheric controls. These acts aren't just violence against enemies, they're violence against the ship itself. Hull breaches, fires, system failures, these affect everyone, regardless of which faction you support. Historical parallels are chilling. Mutinies aboard sailing ships often ended in disaster for everyone, regardless of which side won. The ship that was supposed to carry them to safety became their tomb. A generation ship experiencing internal warfare would follow a similar trajectory, except there's no land to swim to, no rescue ships on the horizon. There's only the void of space and the slow realization that everyone is going to die because they couldn't maintain social cohesion. Let's discuss information control, because this becomes a critical issue over time. The ship's archives contain all of human knowledge that the mission designers deemed important: science, technology, history, culture, everything the crew might need to maintain the ship and establish a colony. But information is power. Whoever controls access to the archives controls knowledge, which confers enormous authority. Over generations, this could lead to the emergence of a knowledge-keeping class, a priesthood of information that controls what others can learn. Imagine a scenario where access to technical manuals becomes restricted. The engineering guild doesn't want untrained people attempting repairs, so they lock down the technical archives. Only certified engineers can access the information. This seems reasonable initially, but over time it becomes a tool of social control. Knowledge becomes hereditary. Engineering families pass their knowledge to their children, maintaining their privileged status. Other families are excluded, creating a rigid class system. Those without access to knowledge become dependent on those who have it. Social mobility disappears, the society stratifies, and resentment festers. Or imagine a darker scenario. The leadership decides that certain historical information is too dangerous to share. Maybe they suppress the history of Earth's wars, genocides, and atrocities, fearing that knowledge of humanity's capacity for evil might inspire similar horrors aboard the ship. So they curate the archives, presenting a sanitized version of history. But information suppression never works perfectly. Fragments of the real history survive, passed down as rumors, forbidden stories. When people eventually discover they've been lied to, trust in authority collapses. Everything the leadership says becomes suspect. If they lied about history, what else are they lying about? The environmental readings, the destination's viability, the mission itself. Let's examine the economic system aboard the ship. because this is rarely yet discussed in detail. On Earth, economies are based on trade, markets, private property, and currency. Money represents value, and people exchange goods and services. But a generation ship isn't a market economy. You can't have competing businesses when there's only one ship. You can't have property rights when every square meter is mission critical. You can't have wealth accumulation when resources are finite and must be allocated for survival. So the ship operates more like a command economy or a resource-sharing collective. Central planning determines resource allocation. Everyone receives housing, food, water, air, medical care according to need and availability. Work assignments are based on the mission's requirements. This sounds egalitarian, and in some ways it is. There's no billionaire class hoarding resources while others starve. But it also means there's no economic incentive, no personal reward for innovation or hard work beyond social recognition. This creates motivational challenges. On Earth, people work for various reasons: survival, wealth accumulation, personal achievement, social status. On a generation ship, survival is guaranteed. Assuming the ship functions, wealth accumulation is impossible, and social status might be the only meaningful reward. But social status in a tiny community is limited and often arbitrary. If hard work doesn't lead to tangible benefits, why work hard? Why innovate? Why do more than the minimum required? Some people are intrinsically motivated. They find meaning in work itself, in excellence, in contributing to something larger. Others need external incentives. In a command economy with no market incentives, productivity can decline over generations. This is one of the reasons command economies on Earth have struggled. Without price signals and profit motives, efficiency decreases, innovation slows, and stagnation sets in. On a generation ship, economic stagnation could be fatal. The mission requires constant maintenance, continuous problem-solving, relentless efficiency. If productivity declines, if innovation stops, the mission fails. Let's talk about something deeply personal: relationships and sexuality in this confined environment. Humans are social creatures with complex emotional and sexual needs. On Earth, if a relationship fails, you can move to a different city, meet new people, start fresh. On a generation ship, you can't escape. If you have a terrible breakup, you still see that person every day. If you're rejected romantically, there's nowhere to process that pain privately. The entire community knows your business. In a population of a few hundred to a few thousand people, the pool of potential partners is small. This creates complicated social dynamics. Romantic competition becomes intense because options are limited. Jealousy, heartbreak, rejection, these normal human experiences become magnified in a confined space. And because the community is small, individual romantic dramas affect everyone. Your breakup isn't just your problem, it's a community disruption. There's also the deeply uncomfortable question of sexual diversity and consent in a controlled environment. Mission designers concerned about genetic diversity might implement reproductive policies, regulations about who can have children, with whom, and how many. This is eugenics, even if motivated by survival rather than ideology. Being told who you can or cannot reproduce with, having your reproductive autonomy controlled by mission authorities, is a profound violation of personal freedom. Yet without some form of reproductive management, genetic diversity problems compound, inbreeding increases, and the population's long-term viability collapses. Some mission designs propose genetic engineering or artificial insemination with stored genetic material to maintain diversity without requiring people to partner with specific individuals. But this raises its own ethical nightmares. Children conceived through artificial insemination with anonymous genetic material don't know their full biological heritage. Families become biological strangers. And genetic engineering, even with the best intentions, risks creating new problems. unexpected genetic interactions, unforeseen health issues, social discrimination against natural versus engineered children. Let's discuss the arrival scenario one more time, but from a different angle. What if they don't want to arrive? We've assumed throughout this analysis that reaching the destination is the goal, that everyone aboard is committed to completing the mission. But what if, after centuries of life aboard the ship, the crew has adapted so completely to space-based existence that a planetary surface seems alien and hostile? Think about it from their perspective. They've lived their entire lives in controlled environments. They know every corridor, every system, every person. The ship is home. It's safe, predictable, familiar. Now they're supposed to land on a planet, a place with unpredictable weather, dangerous wildlife, unknown diseases, open spaces that trigger psychological terror. Why would they want to do that? The original mission was Earth people going to colonize a new planet. But these aren't Earth people anymore. They're ship people, space-adapted humans who've evolved culturally and perhaps even biologically to life aboard the vessel, so they might refuse. They might arrive at the destination system and decide, we're not landing, we're staying aboard the ship, this is our home. And honestly, from their perspective, this might be the rational choice. Landing is dangerous, unknown, requiring them to start over with enormous risks. Staying aboard the ship means continuing the existence they know, using the destination star's resources to maintain and expand the ship, perhaps harvesting water and minerals from asteroids and moons, but never landing on the planet. This scenario, a generation ship that refuses to complete its mission, is a kind of philosophical failure. The ship didn't fail mechanically or socially. It succeeded in creating a sustainable space-based civilization, but it failed to accomplish its stated purpose because the people aboard redefined what success means. Is this a tragedy, a triumph, a strange hybrid of both? There's also the possibility that the ship arrives only to find that the destination planet is already inhabited by intelligent life, not just microbes, but civilization. Maybe the planet developed intelligent life independently. Maybe another species beat humanity to this star system and has already established a presence. Now what? The human crew expected to colonize an empty world. Instead, they're potential invaders arriving in someone else's home system. Do they attempt peaceful contact? Do they request permission to settle? What if the indigenous species refuses, viewing the humans as threats or contaminants? What if the indigenous species is hostile, technologically advanced, and views the generation ship as an intrusion to be destroyed? The crew has no weapons capable of defending against an advanced civilization. They have no diplomatic experience, no understanding of alien psychology or communication. They're profoundly vulnerable. Or consider an even stranger scenario. They arrive to find ruins, ancient structures, evidence of a civilization that once existed on the target planet but is now extinct. This raises terrifying questions. What killed them? Environmental catastrophe? War? Disease? Resource depletion? Whatever destroyed the previous civilization might still be present, waiting to destroy the human colonists. Do they proceed with colonization knowing that something, some environmental factor, some planetary danger wiped out a previous intelligent species? Or do they retreat, searching for another destination, condemning themselves to more centuries or millennia of travel? Let's talk about the psychological weight of failure. If, after centuries of travel, after generations of sacrifice, the mission fails, the ship is damaged beyond repair, or the destination is uninhabitable, or the crew is dying from radiation or disease, how do the final survivors cope psychologically? They know their entire civilization's existence was for nothing. All the suffering, all the deaths, all the sacrifices were wasted. The mission their ancestors began with hope and determination ends in futility and extinction. the psychological impact of that realization would be devastating. Some might find consolation in having tried, in having pushed the boundaries of human possibility, even in failure. Others would be consumed by despair, by the meaninglessness of their existence. The final generation would die knowing they are the last, that everything and everyone they've known will vanish without legacy, without accomplishment, without even a grave marker to acknowledge they existed. This brings us to perhaps the deepest question: is it ethical to begin such a mission in the first place? The people who design and launch a generation ship won't experience the consequences. They'll die long before the mission succeeds or fails. The people who do experience the consequences, the middle generations, the ones living between departure and arrival, never consented to participate. They were born into the mission, their lives constrained and defined by decisions made by people long dead. Is it moral to create lives under these conditions? To bring children into existence knowing they'll live in confinement, with limited freedom, elevated disease risk, psychological stress, and all for a mission they didn't choose. Some philosophers argue that this is categorically unethical, that it violates the autonomy and dignity of the people who will be born into the mission. Others argue that if the mission has sufficient value, preserving human civilization, establishing humanity as a multi-star species, the sacrifice is justified. But here's the uncomfortable truth: we can't know if it's justified until the mission succeeds or fails. And the people making that determination, the ones experiencing the consequences, can't give informed consent because they don't exist yet when the decision is made. This is an ethical paradox with no clean resolution. Let me bring this to a close by acknowledging something important. Despite everything I've said, despite this litany of horrors and failure modes, I don't think generation ships are impossible. I think they're extraordinarily difficult, far more difficult than most people realize. I think the engineering challenges, while immense, might eventually be solvable with sufficient technological advancement. But the social, psychological, and ethical challenges are harder than the engineering. You can't engineer human nature. You can't design away psychological stress, social conflict, existential despair. If humanity ever does attempt generation ships, success will require not just technological mastery, but profound wisdom about human nature, society, psychology, ethics. It will require designing social systems resilient enough to survive centuries of isolation and stress. It will require creating cultures that maintain purpose and cohesion across generations who never chose the mission. It will require solving problems we barely understand, even in favorable Earth environments, let alone in the hostile void of space. The people who design such missions will need humility, acknowledging that they cannot predict or control everything, that their plans will be imperfect, that people generations hence will face challenges the designers never imagined. They'll need to build flexibility into the mission, allowing future generations the agency to adapt, modify, or even abandon the mission if circumstances require. And perhaps most importantly, they'll need to ensure that the people born aboard those ships have lives worth living, not merely as instruments of the mission, but as human beings with inherent dignity and value. If generation ships reduce people to mere components serving an abstraction, the mission, the species, the future, then even if they succeed technically, they fail morally. So generation ships are a nightmare. But here's what's worse. The physics of space travel guarantee you're never coming home, no matter what ship you're on. The video on your screen explains exactly why. The real reason interstellar travel is a one-way trip. This one is a must-watch. See you there.